So these are the notes and examples for 5.62 triangle inequalities. So we're going to use what is known as the hinge theorem and its converse. So when you're looking at this, one key thing is that we have to have two sides of one triangle congruent to two sides of another triangle. So this creates our congruent set of hinges to work with. So we have to have the sides of our hinge congruent. So a hinge will open and close. So hinges are on doors and other items. So we have a common hinge between the two triangles. This gives us an included angle. So an included angle is the angle created by our hinge. So in the hinge theorem, we can use the measure of our hinge angle to compare the third side, which is basically the opening across from our hinge. So whatever inequality we use to compare the hinge angles will be the same inequality we use to compare our third sides. The converse also requires that two sides of one triangle congruent to two sides of another. So once again, we have to have congruent sides on our hinges, but this time we use our third side information in order to compare our hinge angle. So whatever inequality we have for the third side, we use the same inequality for the hinge angle. Oh, one more thing is for a right triangle, it doesn't actually fit the hinge theorem exactly. So with a right triangle, you won't actually be given two sides that are congruent because of the way the sides work in a right triangle. You will be given a right angle and a pair of congruent legs. So then we can use this to compare the acute hinge angles. So if we have this leg that creates our acute angle and the hypotenuse of our right triangle, we can still use a version of the hinge theorem. So we can base the length of this other leg using that hinge angle or that hinge angle based on the length of this leg. So our first set of problems is completing the statement. So if we have two congruent sides and information about the hinge angles, we can use the hinge theorem. If we have two congruent sides and information about the third sides, then we can use the converse of the hinge theorem. We also end up using congruent triangles and the fact that corresponding parts are congruent. So in our first question, we have our hinge. So we have our first set of congruent sides and our second set of congruent sides in order to create our hinge. And then we're looking at our side lengths or what we're trying to compare. So we're trying to compare these side lengths of AB and DE. We don't have measurements for those, so we use the angles opposite them. Opposite the AB is a 105-degree angle. Opposite DE is a 110-degree angle. And we use the same inequality symbol for the numbers that we do for the sides. So since 105 is less than 110, the length of AB is less than DE. So in the next one, once again, we have our hinge. So our two sets of congruent sides to make our congruent hinge. And then when we look at this one, once again, we're trying to get a comparison for the third side. And we have the angle information. Both of the angles are 117 degrees. This actually turns out to be congruent triangles by side, angle, side congruence. So corresponding parts are congruent or equal to each other. Problem 3 is that special circumstance of the right triangle. So instead of having a complete hinge, we have one pair of congruent sides in a right triangle. So we use the hypotenuse of the right triangle to complete our hinge. So this time we're looking for the angle measurement comparisons. So we're going to use the sides that are across from them. So across from 2 is a side that's 8. Opposite 1 is a side that's 7. And we use the same inequality for both. So since 7 is less than 8, the measure of angle 1 is less than the measure of angle 2. Problem 4, once again, wants us to compare angles 1 and 2. So we find our hinge. So we have our set of congruent sides, and we have our shared side to get our congruent hinge sides. And then we look at this one. So we are going to use our sides opposite them in order to compare those angles. And it turns out that the sides opposite them are exactly the same. So this turns out to actually be congruent triangles by side, side, side congruence. And since 6 is equal to 6, our corresponding parts of angles 1 and 2 are also equal. In the next one, we're looking to find the measure of angle or side MS compared to LS. So when we look at our hinge, we have our single marked side, we have our shared side. So that creates our hinge, and we can use the hinge theorem and use these angles. So the 95 degrees is in the same triangle as MS. The 98 is opposite the LS. And then we just use the same inequality. 95 is less than 98. So the length of MS is less than the length of LS. In the next one, we're trying to compare angles 2 and 1. So we look for that congruent hinge sides. So we have our single marked sides and our shared side to get our hinges. And then we use the converse of the hinge theorem. So opposite angle 1 is a side that's 8. Opposite angle 2 is a side that's 7. And we use the same inequality for our angles as we do for the sides. 8 is greater than 7. So the measure of angle 1 is greater than the measure of angle 2. In our matching problems, the biggest challenge is actually figuring out our triangles. So we have to locate the triangles, and then we explain our reasoning. Our reasoning is pretty much going to be the hinge theorem or its converse or congruent triangles. So the hinge theorem, its converse or congruent triangles. I'm going to go through and redraw this triangle specific to each question. So we're going to start with problem 7. In problem 7, I'm looking for the triangle that has AB and BC, and the triangle that has angles 1 and 2 with another common side. So for problem 7, I'm going to use this set of information. So I'm going to redraw that. So I have my A, B, C, E, and I have my angle 1 and 2 that we're comparing. So since we have the angle information, I'm going to use the hinge theorem. So we have our hinge. So my set of sides that were identified as being congruent and the shared side will complete my hinge. So since I have the angle information, I can get the side information. So since the measure of angle 1 is greater than the measure of angle 2, we can get the opposite sides of AE and EC with the same inequality. And this happens to be answer choice D. Problem 8. So I'm going to look for the triangle that has AE and EC, as well as AD and CD. So with this one, we're working with these two triangles. So I'm going to do a quick redraw of that information. So we have A, D, C, and E. We have information about an inequality with the set of sides, and we have congruent sides and a shared side. So this means the angles that I need to look at from this are the angles 7 and 8. So we are looking at a problem that gives us side information, and we're going to get angle information. So this is going to use the converse of the hinge theorem. So we have an inequality saying that AE is greater than EC. And when we go with the opposite AE is the measure of angle 7, opposite EC is the measure of angle 8, and we use the same inequality. And this happens to be the statement in A. Problem 9, when we look at our triangles, we're looking for angle 9 and 10. So 9 and 10 with BE and ED. So 9, 10, BE, and ED is going to be those two triangles there at the top. So if I redraw this out, if I draw it like it looks, so I have my A to B, B to E, E to D, and D to A. So A, B, E, D. And we have information about 9 and 10. So when we look at the hinge, we were given that BE and ED were equal in length, and we have that common shared side. So when we look at this one, we have the information about the angles. So this is going to be the hinge theorem. We know that the measure of angle 9 is less than the measure of angle 10. So we're going to get the information about the opposite sides. So opposite angle 9 is AB. Opposite angle 10 is AD. And we use the same inequality. Now, you're going to see that this is not actually one of the answer choices. So when you see the answer choice actually says that AD is greater than AB. These two are equivalent statements because the inequality is pointing to the same thing and open to the same thing in both of them. So this is actually answer choice B. So problem 10 is our final question. In problem 10, we're looking at a triangle that has AB and BC and AD and DC. Process of elimination, you've pretty much figured this one out already. So we have our two triangles. It turns out that these triangles are not actually completed in the picture itself. So we have the A, we have the B, we have the C and the D, but there is not a one true segment that goes from B to D in the diagram. So when we look at our information on this particular picture, we have that AB and BC are congruent. We also have that AD and CD are congruent, and it turns out that we have this set of sides congruent. So this is actually congruent triangles by side, 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 and corresponding parts of congruent triangles are congruent. Now, the confusion happens with the way they have those numbered. So the angles that they're talking about are the measure of angle 3 plus 4. So that's actually the measure of angle BAD. And then they say angle 5 plus 6, which is actually the measure of angle BCD. So this one is answer choice C. In the last set of examples, we're supposed to use an inequality to describe the restrictions on the value of x using the hinge theorem or its converse. So if they tell you the angle measures, it's the hinge theorem. If our variable is in the angle measures, we use the converse of the hinge theorem. So if we have the angle measures and the variable is on the side, it's the hinge theorem. And if we have numbers for our sides and variables for our angles, it's the converse of the hinge theorem. So what we're going to do is we're going to set up an inequality with our known information and then get the opposite with the same inequality and solve. So in the first problem, we find our hinge. So there are two sides that measure 6, and then we have the common side between our angles. So we compare the angles. 65 degrees is less than 70 degrees. And then we get the sides that are opposite them. So opposite the 65 is the 7. Opposite the 70 is the x. And the key to the hinge theorem is to use the same inequality. So now this is the portion that we solve. And there's really nothing else to do to solve this problem. The x is already by itself. Now, there are some of you who don't like to leave the variable on the right side. Just keep in mind that if you want to switch up the variable and the number, that you also have to switch the inequality. It should still point to the same thing and it should still open the same thing. So you can either write it as 7 is less than x or x is greater than 7. In the next problem, we have the hinge. So we have our two congruent sides with the common side, and we have the side measurements. So we compare the sides. 6 is less than 7, and then we get the angles across from them. Opposite the 6 is our angle x plus 3. Opposite the 7 is the angle 2x minus 4. And the key to the theorem is whatever inequality we use for the sides, we use the same thing for the angles. Now, this is the part that we need to solve. So we're going to subtract 1x from both sides, and we're going to add the 4 to both sides. Addition has no impact on the inequality symbol. So this ends up being 7, and this ends up being 1x. And we don't actually have to write the 1, so 7 is less than x ends up being our final answer for this one as well. Okay, the next one. We look at this one carefully and we see that we can find two sides that are 12 on our triangles, and we have that common side on our triangles to complete the hinge. So we can use the hinge theorem. We have that 30 degrees is less than 38 degrees. Those are our hinge angles. And our theorem says to get the opposite information and compare it the same way. So opposite the 30 degrees is 3x plus 2. Opposite the 38 is 12x minus 7. And the key to the theorem is we use the same inequality. So this is what we have to solve. Okay, now for those of you who like to have your variable on the left-hand side of the problem, just be careful. If you want your variable to go to the left-hand side of the problem and your constants to be on the right-hand side of the problem, this is going to give us a 9x less than -9. And when I go to divide by -9, this is where I have to be careful because this is a negative number. It's going to impact what happens with this inequality symbol. Because I'm dividing by a negative number, the inequality symbol has to flip over, and we end up with x is greater than 1. So be careful when solving an inequality. Your inequality symbol stays exactly the same unless you're dividing or multiplying both sides by a negative number.